Yes, screen is visible. Screen is visible or not?
Yes, sir.
Yes, sir.
Okay, yeah. So yesterday we discussed about the uh, what is that N type and P type charge carriers. Okay, concentration of P type charge carriers. Okay, so we discussed in last class. Okay, now how Fermi level will be depend on P type semiconductors and N type semiconductors also we will discuss. So with temperature as well as concentration. Okay, so those are the important. So along with the question they will ask how Fermi level will be depends on the with the temperature. Okay, sometimes they will ask only about the concentration. If increase the concentration, what happened? Decrease the concentration, what happened? They will ask like that. Okay, so on the basis of like that, you have to study. Okay, so practice. So whatever we have main three important questions we discussed in last three classes. So what are those means? In case of intrinsic semiconductors, intrinsic semiconductor, density of holes and density of electrons we discussed. So in case of intrinsic semiconductor, total charge carriers means we have to take Ni is equal to under root of N into P we have to calculate. So that is the total question. So both we have to, so they will ask charge carriers in case of intrinsic semiconductor means you have to solve the density of holes as well as density of electrons, and finally you have to derive the equation Ni is equal to under root of N into P. Okay, so that is in case of intrinsic semiconductor. If they ask so extrinsic semiconductors, extrinsic, so charge carriers in extrinsic semiconductor means they will ask specifically either N type or P type. Okay, so depends on that. So you solve that. Okay, now we are discussing about the Hall effect. Okay, Hall effect here. So Hall effect is the so one application. Okay, so now we are discussing about the Hall effect. So what is the Hall effect definition? First we will discuss. Okay, so when a magnetic field is applied perpendicular to the current carrying conductor or semiconductor, voltage is developed across the specimen in a direction perpendicular to the both current and magnetic field. This phenomena is called as Hall effect, and the voltage developed is called Hall voltage. Okay, so once again I will explain you what is the Hall effect. So first of all we will take any material, either it will be semiconductor or conductor, either it will be semiconductor or conductor. So at a particular direction current flowing through that semiconductor or conductor. Okay, so now we will apply the magnetic field, we will apply the magnetic field to that conductor, magnetic field to that conductor. Okay, so that magnetic field direction is perpendicular to the current direction. Applied magnetic field direction is perpendicular to the current direction. Okay, now what happened means, so after applying the magnetic field, voltage will be developed, voltage will be developed perpendicular to the both current as well as magnetic field. Okay, so first of all, so we are taking one material, in that material current is passing, current is passing in a particular direction. Now what we are doing means, now we will apply the some magnetic field. That applied magnetic field direction is perpendicular to the current direction. Now what happened means, after applying the magnetic field, voltage will be developed, voltage will be developed. So that developed voltage is perpendicular to the both magnetic field and current. Okay, so this is about the Hall effect definition. Okay, for that let us consider a thin rectangular specimen carrying a current I in x direction. So we are taking here rectangular specimen. So in that current is carrying. So that current carrying direction is x direction. X direction. Now what we are doing means, now we are applying the magnetic field B. Okay, which is the y direction. Magnetic field direction is y direction. So now according to the Hall effect, what happened? Potential difference VH is developed. So what is that direction means? Along the z direction, because so x y z, so both are mutually perpendicular with each other. Okay, so that means here voltage direction is perpendicular to the x and y directions. Okay, now so let us see the diagram. So this is here, so one rectangular specimen. So now current carrying along the x-axis, current is flowing along the x-axis. Now we are applying the magnetic field outward the here screen, outward the screen. Okay, so current direction is so right side, current direction of the specimen is right side. So applied magnetic field is what is that, outward the screen. Okay, now what is the direction of, uh, potential, what is that, so developed potential developed. So in which direction potential will be developed? So in which direction it will be developed? Okay, so now I will explain you. So here some current is passing according to the Lagrange, according to the Lagrange. So what happen if current is passing in any specimen? If you apply the magnetic field, what happen? Some force will be occur on a, so that charge carrier, whatever the charge carrier, either hole or electron, whatever it will be. Suppose some charge carrier is moving inside the specimen, now if you apply the magnetic field, what happen? Some force is developed, some forces act on the charge carrier due to the magnetic field, okay. So that's why what happened, so that uh, the charge carrier shifts depends on the force direction, okay. So and what is the force direction? Now I will explain you. So if you so take the left hand, so keep four fingers so perpendicular with each other. So my fingers are visible or not visible?
No, sir.
Okay, so 1 minute. Yeah, now visible fingers are visible.
Yes, sir.
Yeah, so I am keeping these four fingers perpendicular with each other, so first one is this is the force, second finger is what is that, magnetic field. So third finger is current. Simply how you will remember means FBI. So thumb finger is force, okay. So this index finger is what is that, magnetic field direction. So this forefinger is middle finger is what is that, current direction, okay. Simply how you will remember means FBI, force, magnetic field, current, FBI, okay. Now I am placing, so according to, so previously how we will take, so x-axis current direction, and so what is that, magnetic field applied in which direction? So that means outward to the screen, see here. Current direction. So so this second finger, that means this finger shows the, index finger shows the, what is that, magnetic field direction, and this thumb finger shows the, what is that, force direction. See here, so this is the current direction, so this is the magnetic field direction. What is the force direction? Downward direction. See this, downward direction, because so current direction is this one, so magnetic field direction is this one. So now what is the force direction? Downward direction, okay. So like that, by using so these what is that, left hand rule, we can so calculate the direction. So how you will remember what is the, which denotes means FBI. So thumb finger explains the thumb finger explains the force, so index finger explains the direction of the magnetic field, okay. Middle finger explains the direction of the current, FBI, like SBI, instead of S we are taking FBI, okay, like that. So we can explain the, so direction of the force, in which direction it will be acting on, okay. Yes, now it is, screen is visible. So here So this current is carrying along the x direction. Now magnetic field direction is outward the screen. Okay, now force direction is so downwards, so downward direction. Okay, see here. So due to magnetic field B, there is a Lorentz force act on a each electron. Okay, so if electron is moving inside the magnetic field, if electron is moving inside the magnetic field, some force will be acting on that electron. So what is that force means? F is equal to B into E into V. Okay, B is the applied magnetic field. So FB is equal to B into E into V. Okay, so B is the applied magnetic field. E is the charge of the electron or hole. So whatever the charge carrier we are taking. Okay, now so V is the velocity of the electron. V is the velocity of the electron or hole, whatever we are taking here. Okay, so now what is the force acting means? F is equal to BeV. So what is the direction of force is? Downwards direction. Downwards direction. Downwards direction means this is along the z axis. Okay, so now mutually perpendicular. So these three. Okay, now see here. So now all electrons are coming downward. See here, so because after applying the magnetic field, what happened? Electrons are, so force will be acting on downward direction. That's why, so electrons comes to the downward direction. That's why what happened? Potential difference developed between the, so phase 1 and phase 2. Here two phases are there. So for the two phases, some potential will develop, difference will be developed. Okay, so because all charge carriers, electrons are accumulated in downward direction. If electrons are coming downward direction means, so positive charge is accumulated on, so opposite direction. Positive charge is accumulated on opposite direction. So that's why what happened? Some potential difference will be developed in a two phases, opposite phases. Okay, so due to that potential difference, yeah. So what is that potential difference? So due to that potential difference, what happened? Some electric field will be occurs. So due to that potential difference, some electric field will be occur. So along the y-axis, okay, yeah. So due to along the negative y direction, due to along the negative y direction, so the force. So due to this electric field, what happened here? 1 minute. Yeah. So some electrons will be downward. So due to that, what is that shifting of charge carriers? What happened? So positive charge is developed on opposite direction, negative charge is developed in below direction. So that's why some potential difference will be occur. So due to that potential difference, so electric field will be occur. Electric field will be occur. So due to that electric field, so what happened? If you apply the electric field, so what happened? Force will be occurs. Due to that electric field also, some force will be happen. Okay, some force will be happen. That force direction is opposite direction to the, so whatever the previous direction will be there na, so F is equal to BeV. So this direction is downward direction. Now so due to the electric field, here, what happens? Some force will be occur. What is that force means? So F is equal to E into EH. EH is the electric field developed. EH is the electric field developed in two phases. So how electric field? There is a relation between potential and electric field. I will explain that relation also. So due to this electric field also, some force will be act on the electron. That force is F equal to E into E is the charge of the electron and EH. Okay, force due to the electric field, some force will be occur. That force is equal to this one. This force direction. So this force direction is opposite direction to the what is that magnetic field. So due to magnetic field, some force will be occur. That equal to F is equal to BeV. Okay, due to electric field here. Some force will be occur on a electron. So that force equal to E into EH. So the direction of the force will be opposite direction of the magnetic field. So magnetic field force direction. Okay, due to magnetic field, so force equal to BeV. And if you will take at equilibrium condition, at equilibrium condition. Equilibrium condition, what happened? So that means that equilibrium condition occur so at a particular time. At a particular time, okay, at that situation, so electron will be constant. It does not move and upward and downward. Okay, so at equilibrium position, so force occurred due to the electric field is equal to the so force occurred due to the magnetic field. So that means so upward force along the upward direction is equal to the force along the downward direction. So that equal to F of B is equal to F of E. So here direction is opposite. That's why I am taking here minus. Okay. So both forces are equal at equilibrium position. Both forces are equal, and so those direction will be opposite in direction. So that's why I am taking minus here. Okay, now, so from this equation, V is equal to how we can write E gets cancelled. So V is equal to EH by B. So V is the velocity of the electron. EH is the electric field developed. That is the Hall electric field. Hall electric field. B is the applied magnetic field. Okay. Now, so V is equal to minus EH by B. Okay. Let us take this is equation number 1. Okay. Now, uh, current density. So current density formula J is equal to NeV. So in that current is passing to the specimen. Current is passing through the specimen means so there is a current density will be there. That current density J is equal to N into E into V. V is the velocity of the electron, E is the charge of the electron, N is the density of the charge carriers. Density of the charge carriers. If you take electron means that is the density of the electron. Okay. So simply so J is equal to current density J is equal to NE into V. Okay, from this, so we can calculate the V. So V equal to J by NE. J by NE. Let us take this is equation number 2. So from equation 1 and 2. Equation 1 and 2. So velocities, so we can equate the both velocities. Okay, we are calculating the velocity. So by using first equation and second equation. So here we are equating both. Okay, now so EH by B is equal to minus J by NE. Minus J by NE. Okay. So now from this we are calculating the Hall electric field. EH is equal to minus JB by NE. Minus JB by NE. So I send the B value this side. Okay. Now this is EH. EH is equal to minus JB by NE. Here, so minus 1 by NE. Minus 1 by NE is called as Hall coefficient. So minus 1 by NE is called as Hall coefficient. That equal to, we are taking RH. RH is equal to minus 1 by NE. So RH is equal to here minus 1 by NE. Substitute that RH value here. Okay. So finally equation will become, so Hall electric field EH is equal to RH into BJ. So B is the applied magnetic field, J is the current density, RH is the Hall coefficient. Hall coefficient. Okay, EH is the Hall electric field. Okay, this is about the Hall electric field. Now we will calculate the Hall voltage. Hall voltage. Okay.
Sir,
Yes.
sir, can you repeat what is meant by E and V, sir?
Yeah. So here small e is nothing but charge of the electron. V is the velocity of the electron.
Okay,
Okay.
sir. Thank you, sir.
Yeah. So velocity of the electron. So for calculating the current density, J is equal to N into E into V. Okay. From this formula, we are calculating velocity. V is equal to J by NE. Okay. So previously, so by using this equation also, velocity of the electron we are calculated. So V is, so charge of the electron both cancel. So V is equal to minus H by B. Okay. Now, so we are equating these two. Equation 1 and 2. Okay, from this we are calculating EH is the, what is that, Hall electric field. So Hall electric field EH is equal to minus JB by NE. Here 1 by NE is called as Hall coefficient, that equal to RH. Okay, so RH is equal to minus 1 by NE. So therefore EH is equal to RH into B into J. Okay, so this is about the Hall electric field. Now we are calculating the So Hall voltage. So this is Hall electric field. So now we have to calculate the Hall voltage. Before going to the Hall voltage, so I will explain you what is the RH. Okay. So consider here. So what is the RH value also in terms of Hall voltage? So RH value in terms of Hall voltage. Okay. So RH Hall coefficient RH is equal to EH by B into J. Okay, this is the RH value in terms of Hall electric field. Okay, now so we can calculate the VH is the Hall voltage. Hall voltage. So there is a relation between voltage and electric field. There is a relation between voltage and electric field. So voltage V is equal to electric field into thickness of the specimen. Thickness of the specimen. Okay, see here. So we are taking, this is the specimen. So this specimen thickness is T. So thickness of specimen is T here. Okay, so now how to calculate the voltage developed across this means, so electric field E into volt, so voltage, so the thick, yes, this formula will be there here. So that formula V is equal to electric field E into thickness T. So voltage V is equal to E into T. Okay, so now Hall voltage VH is equal to EH into T. EH is the Hall electric field. So T is the thickness of the specimen. Okay, so now so from this, so EH is equal to VH by T. Okay, so here, uh, so we have to write this T is in another terms. Okay, so now for that what I am doing means, if B is the width of the sample or width of the specimen. Okay, so here, so B is the width. So I am taking, so here, so T is the thickness, B is the width of the specimen. B is the width of the specimen. Okay, so that means this is 3 dimension. So here, so thickness will be there, width will be there, length will be there. Okay, so T is the thickness, B is the width of the specimen. If you want area, so area means area is equal to breadth into thickness now. So area A is equal to breadth into thickness. Okay, A is equal to B into T. B into T. Okay, so from this, so now we can also call, so current density. Current density previously J is equal to NEV, we call that. So current density formula actually J is equal to I by A. I by A. Okay, so current density J is equal to I by A. So that means current passing through the unit area is called as current density. Current passing through the unit area is called as current density. Okay, so current density J is equal to I by A. So but we know that I is equal to B into T. B into T. Substitute that value here. So now J is equal to I by B into T. Okay. So now here, so RH is equal to, RH is equal to, already we know that EH by, so this formula will be there, B into J. RH is equal to, so EH by B into J. So in this formula we are substituting this J value as well as EH value. EH value. So now RH is equal to, EH is equal to VH by T, and so here B into J. J is equal to I by B into T. Okay. If you simplify it, TT gets cancelled. So simply RH is equal to VH into B into, sorry, yeah. So RH into, sorry, RH is equal to VH into B. VH into B. So by B into I. B into I. So this is the, what is that, Hall coefficient, RH value. Hall coefficient in terms of Hall voltage. Hall coefficient in terms of Hall voltage. So Hall coefficient RH is equal to VH into B by, so B into I. So B is the magnetic, applied magnetic field, I is the current. So here B is the breadth. Okay, VH is the Hall voltage. Hall voltage. So from this Hall voltage VH is equal to B into I into RH by B. So this is the Hall voltage, so formula, Hall voltage formula. Okay, so by using Hall effect, so we are calculating the, so Hall coefficient RH and Hall voltage VH. VH. So what is the use of this Hall effect? What is the use of this Hall effect? Okay, now we will discuss about the applications of Hall effect. Hall effect is widely used in various fields. for a variety of applications. In almost all cases, Hall effect sensors are employed. Okay, so that means by using this Hall effect, we can use it as a sensor. By using, so that semiconductor material used as a sensor. So based on the Hall effect. Okay, Hall effect sensors is transducer that produces its output change in response to changes in the magnetic field. That means if magnetic field will be changes, magnetic field will be changes means what happen? So either Hall voltage will be changes as well as Hall coefficient will be changes. Okay, so based on this formula, based on so this formula, we can detect the change in the magnetic field. We can detect, so we can simply we can measure the so voltage so by using voltmeter we can measure the voltage. Okay, so if any change will be voltage, if you any in that specimen, okay, so there will be change in magnetic field. So based on this phenomena we can measure the so magnetic fields, so response of magnetic field, how magnetic field are changing, how magnetic field are changing. So by using Hall effect we can measure. Okay, that is the first application. And determination of type of given semiconductor. Okay, so now previously, so depends on the type of semiconductor. So based on the RH value, based on the RH value, so if RH is equal to positive, so one type of semiconductor, RH is negative, so one type of semiconductor. So here it will be formula will be there na. So what is that? RH is equal to minus 1 by Ne. Okay, so here N is the density of the electron. If you will take holes, if you will take holes, instead of N, we are taking P. We are taking P. Okay, RH is equal to minus, so that is in that case minus will not come. So RH is equal to 1 by P into E. Okay, in case of electrons, so minus RH will be negative. In case of holes, RH will be positive. Okay, so for that, for N type, for N type Hall coefficient RH is negative. So N type means what are the majority charge carriers? Electrons are the majority charge carriers. That's why Hall coefficient will be negative. For P type semiconductor, Hall coefficient RH is positive. RH is positive. Okay, so by using so this Hall effect we can also determine the so carrier concentration of the holes or electrons. Okay, by using, so by using this Hall coefficient we can also calculate the so carrier concentration of so electron as well as hole. Okay, that formula equal P is equal to N equal to 1 by RH into E. So how to calculate RH means, so by using this formula. So by using this formula, RH is equal to VH into B into so by capital B into I. This by using this formula we can calculate the RH here. So so if you know the RH means, we also know that so carrier concentration, how many electrons, so number of charge carriers will be there. Okay, so either it will be N type or P type. So we can calculate very easily. So by using this formula. Okay. Next, so by using this formula, we can also calculate the mobility of charge carriers. So that means how much. So mobility is nothing but so whether charge carriers are moving or not. So if charge carriers are moving, so that means so that mobility is high. Yeah. So yes, my screen is visible. Students, response
Yes,
one.
sir.
Okay. So now we are calculating the determination of mobility of charge carriers. So what is the mobility means? So how much fast electrons are moving. If you will take metals, so electrons move very fastly. If you will take insulators, electrons so does not move. So that means so we can calculate the mobility. We can calculate the mobility of the charge carriers. So mobility of charge carriers formula equal to so RH into sigma. RH into sigma. Already we know that yesterday we know that formula sigma is equal to Ne into mu. Ne into mu. From that formula, we are deriving here mobility. Sigma is equal to, what is the sigma conductivity formula? Conductivity sigma is equal to mu Ne into mu. So here mobility mu is equal to sigma by Ne. But we know that 1 by Ne equal to RH. So therefore mobility mu equal to RH into sigma. RH into sigma. So this is the mobility. Here substituting the RH value. So previously whatever we calculated, so that RH equal to VH into B by, so B into I. Okay, this formula. So by using this formula, we can also calculate the mobility of the charge carriers. Mobility of the charge carriers. These are the applications of Hall effect. So what is the first application? So by using Hall coefficient, so we can also calculate the, so what is that magnetic field, change of the magnetic field. So either it will be strong magnetic field or weak magnetic field. So based on that, what happened? So we can calculate that. So this by using Hall coefficient or Hall voltage, we can calculate the, so this magnetic field. Okay, second one is the determination of type of semiconductor. So whether it will be, so P type or N type semiconductor. How we can measure means, for N type semiconductor, so Hall coefficient will be negative. So that means if charge carriers are the electrons, Hall coefficient will be negative. If charge carriers are holes, Hall coefficient will be positive. That means it will be P type, means Hall coefficient will be positive. And the determination of carrier concentration. So by using this equation, we can also determine the, so how many charge carriers will be present, whether it will be holes or electrons. So we can calculate the, so number of charge carriers. Okay. Next one is the determination of the mobility of charge carriers. So these are the applications of Hall effect. Okay. So this is about Hall effect. So once again, I will so explain you briefly. So regarding about the Hall effect. So first of all, definition of the Hall effect. This is the very important one. So without definition means, so you can't do anything. So first of all, you have to know the definition. First of all, so when a magnetic field is applied perpendicular to the current carrying conductor or semiconductor, voltage will be developed across the specimen in the direction perpendicular to the both current and magnetic field. Okay, so based on that, here current I is passing along the x direction, and so we are applying the magnetic field along the z direction. Magnetic field along the z direction, some force is acting on that. Some force is acting on that. Due to that force, what happened? Voltage is developed. So potential difference will be developed. Okay, so what is the formula? Why force is developed means according to the Lorentz. According to the Lorentz. So any charge particle is moving inside the magnetic field. Inside the magnetic field, force will be act on that. Force will be according to the Lorentz. If any charge particle is moving inside the magnetic field, force is acting on the charge particle. Okay, so what is the direction of the charge particle also? So that means if you know what is the direction of the force, what is the direction of the force acting on the charge particle means, if you place the, so your left hand fingers, three fingers perpendicular with each other, thumb finger shows the force direction, and index finger shows the magnetic field direction, and middle finger shows the current direction. Okay, if you place the, so along those direction, so remaining one gives the direction. Okay, suppose if you know the force direction and current direction means, so we can calculate the, so direction of the magnetic field. If you know the magnetic field direction, force direction, we can calculate the current direction. Okay, so that's why, so if you know the any two parameters, we can calculate the other direction. Okay, according to that Lorentz formula. So that means what is the force direction means, that force is acting on the negative y-axis. The force is acting on the negative y-axis. That means downwards direction. Downwards direction. So that force is equal to BeV. Okay, this is Lorentz force. Lorentz force due to magnetic field, some force acting on the charge particle, that equal BeV. Okay, now here, so because of the, so what happened, due to Lorentz force, what happened, charge particles will be displaced. So how it will be displaced means, negative charge particles comes to the downward direction, so positive charge is developed on a upward direction. That's why there is a some potential difference between the phase 1 and phase 2. Due to that potential difference, what happened, some electric field will be occur. Electric field will be developed. So that due to that electric field, some force will be act on. Due to that electric field, some force will be act on. That force equal to, so F E is equal to E into EH. Okay, E is the charge of the electron, EH is the electric field developed, that developed across the faces, across the faces. Okay, so here EH is the Hall electric field. Okay, at the equilibrium position, what is that force due to the magnetic field is equal to the force due to the electric field. Okay, that's why BEV is equal to E into H. So why I am taking minus means here. So both are in opposite direction. Both are in opposite direction. Okay. Now, so here V is equal to from this above equation we are calculating the velocity of the electron. Velocity of the electron V is equal to so EH by B. EH by B. So V is equal to EH by B. Okay. This is, let us take equation 1. Already we know that current density formula J is equal to N into E into V. Okay. From this, so velocity we are calculating V is equal to J by NE. So from equation 1 and 2 we can equate both equations. Okay, so from this we can calculate the EH value, Hall electric field, JB by NE. Okay, so here 1 by minus 1 by NE is called as Hall coefficient. Hall coefficient that equal to RH. Okay, substitute this RH value in above equation. EH is equal to RH into BJ. So this is the Hall electric field in terms of Hall coefficient. Okay, from this, so Hall coefficient RH is equal to EH by BJ. Okay, yeah. So we have to calculate here Hall voltage also. So that's why. So there is a relation will be there. Voltage and electric field, that relation V is equal to E into T. If you apply the above system, so VH is equal to EH into T. Okay, now from this EH is equal to VH by T. Okay, yeah, from here, so I am taking here, so area of the specimen, area of the specimen A is equal to, so breadth into thickness B into T. Okay, so now according to the current density, so formula, current density formula, J is equal to I by A. So I, current density, what is the current density means, so current passing through the unit area. Okay, that equal J is equal to I by A. So from this J is equal to I by BT. So this J value, so J equal to I by BT, and EH value substitute in the, so this equation, so RH equation. Okay, so now RH is equal to VH by, instead of EH, so we are substituting, so voltage, so that equal to VH by T, and instead of current density I am substituting the current here. So that's why J equal to I by BT. Okay, so this equation some terms will be cancelled, so remaining will be RH is equal to VH into B by, so B into I. Okay, this is the Hall coefficient in terms of Hall voltage. Okay, so similarly Hall voltage VH is equal to BI into RH by B. This is the Hall voltage. Okay, so this is the Hall voltage and Hall coefficient, and these are the, so this is the about the Hall effect. This also very important one. This also very important one. So just very simple and so important one also. Okay. So once practice, once read this equation, you can clarify all doubts. Okay, yeah, so I will take the attendance first. If you have any doubts you can ask, any doubts in that, so otherwise you can leave from the session. Any doubts on the Hall effect or previous any topics?